Hey, and we're back to finish chapter 2 today. So we are still looking at section 2.1 and 2.2. We're looking at strain, and this video is going to be all about shear strain. You can notice by the picture right here on our cover slide, when we looked at normal strain, it was that delta, that change in length. We were stretching that rubber band. Now we are going to have a skewing. And if you like turn your head sideways and cut this bread, see how that cross section would skew like that? Pretty easy, okay? So just, again, you all may be tired of this, but normal just means perpendicular. It doesn't matter which direction. Shear just means parallel, okay? It doesn't matter how we cut it. The behavior is going to be normal force, normal stress, normal strain, shear force, shear stress, shear strain, okay? We're going to get kind of a change in angle. So when you look at that final picture of that bolt over there, you can see that the cross section has skewed, okay? It's skewed away, okay? If we look at this rubber bearing pad, we talked about the normal stress, but now we're seeing that skewing of the top displacing relative to the bottom, okay? So shear strain, I think about it like cutting bread. That may not be the right way to think about it, but the perpendicular line segments, okay, like this, shrink, are no longer perpendicular. We have sheared it. We have, pressed across the top of that cross section. If you look at this rubber block right here, we have it loaded so that there is a weight. The force is coming across the top. So again, it's a normal force. It's coming from a normal force, right? There's this mass. Gravity is pulling that mass, so there's a normal force in that cable. Okay, it's coming around the pulley. We've attached it to the top of that rubber block, to the top of the rubber block. So now that normal force has become a shear force. It is parallel to the top of that rubber block. Shrink, and we get that change from a perpendicular to, we now have this angle. That's our shear strain. That's our shear strain, okay? So again, it's a normal force that is created, shear. Very similar again to a bike, brakes on a bike, the rubber pads, you have that compression, but you also have that perpendicular is no longer perpendicular when you look at the rubber pad, and it skews as you're stopping the bike. Bike. It's like this. It goes rink, and we have that skewing from the back of the rubber pad, which is on the levers, and the front of the rubber pad, which is touching the wheel. Okay, so we go from perpendicular to not perpendicular. It's not necessarily uniform. You could have like a curve that's associated with, maybe there's more deformation or more deformation here at the top in terms of it skewing to the right or to the left, and not as much at the bottom. But this block looks like it's pretty uniform distortion. Okay. So there you have it. That's shear strain. It changes from a perpendicular to non-perpendicular. And it's just a force that's acting parallel to the cross section. It can come from that normal force that's pulling it, but it becomes a shear force as it goes across the top. Okay, so we're looking at this again. I know it's the same figure. So we have this axial load. Again, all we're talking about right now are axial loads. They are acting through the centroid perpendicular to our cross section. Okay, it's an external force. We can resist it inside on that wood. It would be a normal P over A, or as it goes across the bolt. Okay, it's a resisting force across the bolt. It's now parallel to the cross section. That's why it's shear. And that's how you end up with that distortion. Okay, as that bolt wants to cut in half, you're getting that distortion across that cross section where it's no longer perpendicular, but it's wanting to skew. Okay, so shear strain, it's a gamma. I guess that's a lowercase gamma, maybe. Average. It's just an average shear strain. Okay, remember we had delta. We had a lowercase d delta, lowercase delta, because we experience small amounts of strain. Here, shear strain, it's a gamma. Shear strain is this angle right in here where I'm pointing, okay? There's lots of ways to find it. The first is if you know the angle that it is tilted over, so not theta prime, but just that angle, that's your gamma. So if I know that it's displaced at the top from 0 to now this top fiber has displaced over 1 inch, and I know that the whole thing is 10 inches tall, well, that's just tangent, opposite, over, so 1 inch over 10. But the beauty about strains that we look at is that we're looking at very, very small strains. So when you're looking at small strains, then we can just say gamma equals that delta x over that length. We don't have to say tan theta and then do delta x over L and then find the radians of that, because with very, very small strains, we can just say it's delta over L. And we don't have to go through find the angle that comes over. It's just, that's all it is. Super, super easy, okay? It's also, what is pi over 2? Pi over 2 is 90 degrees in radians. And if I know the interior angle, okay, I know this interior angle of 75 degrees, then I know gamma has to be 90 minus 75, which is 15 degrees. But I have to make sure I put that in radians. So that's why it's pi over 2 minus theta prime. So I could see that theta prime plus gamma equals 90 degrees. Okay? Again, small strains. When we're looking at the very, very tiny gamma, all we have to do is look at this delta up at the top divided by L. So what would positive and negative be? If gamma is less than 90 degrees, so we've skewed into from 90 degrees in, that is a positive angle decrease. And it's because of this pi over 2 minus theta. So if theta is interior, it's getting smaller than 90, we have a positive number. If gamma is larger than 90, then we have negative. It's negative. So think with me here. If theta prime, if that's the interior change of theta prime is bigger than 90, when I take pi over 2 minus theta prime, which we've skewed this way, so we're now bigger than 90, we're going to get pi over 2 minus bigger than 90 is a negative number. So it tells you I'm either skewing positively in or I'm increasing my angle bigger than 90, and it's a negative increase, okay? Here's another way to look at it if you need to remember. This would be a great thing to put on a 3x5 card as you're doing your homework so that you can see my undeformed body, pi over 2, 90 degrees, but in radians. Deformed body, okay? We have that internal theta, pi over 2 minus theta is gamma, okay? We have the third picture, theta's gotten bigger, pi over 2 minus theta. It's now negative, okay? Bigger, because pi over 2 minus theta is a negative gamma. So shear strain, changing from perpendicular edges to skewed edges. Shear strain. Okay, that's it.